Okay, today I'm going to be presenting an overview of the routing algorithms we support in Omni-Path FM. I'll touch on some of the routing constructs we use as well as the topologies we support. And I'll also touch on some of the constructs we've implemented to aid in adding new routing algorithms. So the Intel Omni-Path FM currently supports shortest path routing algorithm. It supports device group routing, up-down fat tree routing. It supports dimension order routing of mesh and torus fabrics. And it has enhanced hypercube support for hypercube and mesh fabrics. And I'll be getting into these more detail. This is the Omni-Path FM config file. It's XML based. To change a routing algorithm, you would use this section for routing algorithm. Shortest path is our default routing algorithm. It does a good job of static load balancing in agnostic topologies. So out of the box, you don't have to do any other configuration based on topology. Okay, when setting up routing, we have to balance among a number of things. First of all, performance, of course. Avoidance of deadlocks. A number of types of topologies are prone to deadlock, so we have to look at that. Handling fabric disruption. Do we handle it fast enough? When fixing fabric, can we do minimal disruption, meaning don't affect any other areas? And then fabric bring up time. It could be a great algorithm, but if it takes a long time to calculate, that could be a problem. We have something called device group routing in Omni-Path, and what device group routing does is it ensures path diversity within a certain device type. So why would we need this type of routing? So certain patterns in a fabric can lead to patterns in your routing, and this can cause an issue with performance. For instance, in this kind of contrived example we have here, we have compute nodes on the bottom there that are in green, and we have storage in orange, right? I don't know this. Okay, so compute, storage, we ended, if you do a simple round robin, in this case, you could end up routing all of your storage to a single switch, causing some type of saturation there. If you've provisioned the fabric so that different resources are provisioned for each type of device using different VLs, you've compromised that quality of service. So by defining a routing order and defining device groups, we can fix that problem by, for instance, putting all of the compute in a device group, all the storage in a device group, and then routing over them separately. That ensures path diversity, and it leverages the quality of service. Here's an example of how to configure device group routing. In this case, you would have a routing order section here with the different device groups. Now, in this case, we would route over the compute devices first, then the storage, and then the remaining devices after that in the fabric. A device group can be figured with a number of different constructs. We have different types of GUIDs here. System image GUID, node GUID, port GUID. You can use the node description, and you can include other groups in the device group. We have wildcarding on node description names, so that makes it a lot easier to configure some of these if you have a well-formed name for your node descriptor. Okay, next I'm going to talk about deadlock avoidance in some of our algorithms. With credit-based link layer flow control, you can have some topologies that are prone to deadlock. In this case, we have it's a classic example. We have four different types of traffic flows doing turn occurrence. So in this case, you might have traffic stopped here, trying to send here because there's no credits. B wants to send a D through C, but there's no credits here, and it's a classic deadlock around here. And so we have to address this in some of our routing stuff. This can also manifest in a fat tree, where you might have traffic going up and down here and forming another type of a deadlock situation, the same type of deadlock. We have something called spine-first routing in our Omni-Path fabric manager code. And this is used in shortest path and in the device group routing. If the core switch happens to be a director class switch, then we will be using we can use system image GUID to always route up. So the problem with this type of routing is to avoid this type of routing where you go up, down, which is part of that credit loop we saw there. So by always routing up, we will be good. So this is called spine-first routing. As I said, it is in the device group routing and in the shortest path routing. We've extended this to another algorithm called fat tree up-down routing. With fat tree routing, we provide deadlock avoidance by always routing up. And this is done by using topology data, figuring that out during discovery. For instance, if you know your uplinks and your downlinks, you can always route up in the case where there is both up and down routes. This algorithm also calculates trunk groups for some clustering type topologies to leverage more balanced routing on the setup. So what happens? We need some topology data to be configured to understand the type of topology we're looking at, and that's what I'll get into next. So if you have a very well-formed fat tree, you can configure the tier count if all nodes, host switches nodes are on the lowest tier. It's pretty easy to figure out the topology layout. So in this case, you would configure, from the prior example, a 3-tier node count and all HFIs on the same tier. And discovery would walk from the lowest tier up and determine the layout of the fabric. We don't always have a well-formed fat tree. You may have nodes at core. For instance, you may have storage at the top of the tree, and compute down in the subclusters in the bottom. Or you may have a case where you have nodes at other levels of the tree. Or you may have some cases where you have a strange tree where you have different tiers on one side than the other. In this case, you have to provide more data to the algorithm to actually determine the characteristics of the tree. By configuring a core device group, which lists the actual switches that are at the core, we can figure out all that information. So in this algorithm, you would supply the core device group list and also the tier count. There is also a route last here that does some balancing based on device type as well. So you can specify, like I'm going to put storage all in one and we'll route that separately. Now this algorithm also it provides spine first in a fabric that doesn't have director class switches, but it works equally well on both. So the device groups in this case, you would configure a list of node GUIDs for the switches at the root of the tree. Or you could configure using wildcarding on node description. So If you had a well-named core switch, you could just do something like that. We have support for torus topologies as well. For torus topologies, we use dimension order routing for our mesh fabrics. When it's a torus, we also use dateline crossing. So in here, in this case, we'd have a X dateline, a Y dateline here. And if we cross this dateline, we increment VL for deadlock avoidance. So this algorithm requires 2 VLs. And that's by the dateline crossing that we do that. It's a well-balanced algorithm. It's balanced switch to switch for nearest neighbor traffic and across the fabric. An issue with this routing, of course, is if you have some fabric disruption. For instance, we have a node down here, a switch down here. We can't route any longer X, Y. We have to route Y to YX direction. So we do this by introducing a new set of VLs called escape VLs. In this case, you would jump to the new set of VLs on an illegal turn, and you would use that set of new VLs for the remainder of the path. This is a simple case where you just have one turn, but you could have a 3D or 4D or 5D torus here. That would you could use that during the path. So how is this accomplished? Todd had mentioned in a prior discussion about our concept of SC to SC. We've abstracted the SL to VL transitioning through something called the service channel. And we use the service channel transitioning for this. With this mechanism, in the face of disruption, there's no SL change, and there's no need to query for any different path record changes. Okay, so what happens when we have a number of disruptions? In this case, we have a few switches are now missing. Now, if we were going to route around this closest to the disruption, you would have to increment your VLs twice. Since we're using 4 VLs for this, that would cause some pain because we don't have that many VLs. So how do we do this? We've introduced something called fault regions. So if this switch here would be defined to be in a fault region. So this fault region is here. Any switch that is missing more than one neighbor is considered part of a fault region. And when in a fault region, that switch is part of the fabric. I mean, we still use it for routing to it. You can route a valid path through it, X, Y here, you could do that. But we do not use that for routing broken paths. So that helps a lot with minimizing the instance of multiple illegal turns. We have some tools now for checking out whether the credit loops exist in the fabric. In this instance of this example, it was with a 4x4x4 torus, 64 switches, and I think 512 nodes in that fabric. This was a simulated fabric. And you'll see here that it's deadlock free. In this case, we had removed at random over 20% of the switches from the fabric, and with the use of the fault regions, found that it was still deadlock free. So it's one of those validation tests. So our torus routing avoids deadlock. It goes up to 560 torus, and it's kind of a summary of that. We also have something called enhanced hypercube support. With enhanced hypercube support, you can configure port order for routing as well as cost to influence the dimensioned order routing of the fabric. In this case, you would you can see a physical port was assigned virtual port 1 at a cost of 10, and this information is used for setting up the dimension order routing in the master hypercube. It is also balanced by locality so that your nearest neighbor routing is optimized. Omni-Path has a feature called adaptive routing. It's supported in all of our routing algorithms. And what it does is the fabric manager will supply a list of alternate routes for all lids in the fabric. And the switch firmware will adjust routes as needed. So medium grain, meaning it's done in the switch, not the hardware. And so the switch will monitor for congestion, and in the event of congestion, it will route around using different packets, different paths. It's also used for fixing a path in the face of disruption. If you have a lost path, one of your ports goes down on the switch, we can quickly modify the routing tables at the switch level instead of waiting for the fabric manager to resweep the fabric and reprogram. So it helps with that. We have something called routing modules in Omni-Path. A routing module is an abstraction that is used to implement different types of routing algorithms. There'll be a routing module for fat tree, there'll be a routing module for door. And it's essentially decouples some of the constructs required to be set up based on topology, such as routing discovery. During discovery process, you'll want to walk the fabric in a fat tree and figure out what the topology looks like. Of course, you'll need different routing algorithms, so there's abstractions for routing and different abstractions for quality of service. So essentially, from the mainline code, you would call into this routing module and instantiate the one that is actually configured. And so this is a way to easily add a new routing module to our fabric manager. And I talk very fast, so I believe I'm done. Thank you. Any questions?
Yeah, I have a couple. You mentioned up, down, and fat tree in one sentence. So that's one single algorithm?
Yeah, there's two components to it. Up, down is part of it.
Okay.
Yeah, part of that is up, down. We do enforce that for deadlock avoidance. The fat tree part of it is, we've optimized it to take into account like multiple ISLs in a trunk group going to different switches in a subcluster. So we do a better job of routing in that case.
Okay.
Yeah.
And then your device group routing, is that like an overlay over any other routing algorithm?
Good question. It is an overlay over shortest path, definitely.
So it only applies to shortest path?
It does, but like I said, we have flavors of it in all of your other algorithms. So, so right here, for the fat tree routing, we can say, for fat tree routing, it does a really good job of routing switch to switch. Some of the device group routing is to try to get, it balanced across, your nearest neighbor. This does a good job of routing switch to switch as well as does door. And so, but it does allow us to specify a device class that you want to route separately. And because it has so much balance, one's really enough, and it's a more complicated algorithm to, it's kind of like balancing act, like how much do you want to set up for timing. Yeah. And
then the last question is, I have another one, but I can't remember what it is. So the last question is there visibility into your routing? And what I mean by that is we've had issues in the past with routing where it was advertised as being balanced, but when we actually dumped the routing, it was not. So is there a way to do that sort of thing?
We have tools in our fast fabric, in our OPA report. This was the the one I had for torus, that tool here, this OPA report tool. We also have path usage reporting. And so you can actually use the path usage tool, and it'll walk the fabric and analyze how many paths are used on all the I cells and see how balanced it is. We use it all the time to, like, verify that it's all laid out properly. Yeah.
So you touched on adaptive.
Mm-hmm.
Have you done anything with injection rate limiting?
Injection rate limiting.
So there's
Yeah, some, but maybe we can talk later on that
Okay.
with time. Yeah.
I remembered my question.
Mm-hmm.
The spine first routing, you
Yeah.
were saying it only applies to, well,
Mm-hmm.
I'm asking if it only applies to director class chassis switches. I mean, I'm not sure if you'd ever build 3 levels with edge switches, but if you did,
Right.
could you still use that by just defining where your spines were?
If I was building a 3-level, I would use a fat tree. The spine first, defining something shortest path is an easy way to route fat trees. It is, right, and it's for device group routing, and it's could be used for fat tree, but that also has a up-down detection. And as far as the injection rate stuff, we have some tools for that, but I'm not well versed in it, so we can talk later. Any other questions?
Great, thank you.